Acceleration, in physics, is the rate of change of velocity of an object. An object's acceleration is the net result of any and all forces acting on the object, as described by Newton's second law. The SI unit for acceleration is meter per second squared. Accelerations are vector quantities and add according to the parallelogram law. As a vector, the calculated net force is equal to the product of the object's mass and the acceleration. If the car turns, there is an acceleration toward a new direction. For this example, we can call the accelerating of the car forward a linear acceleration, which passengers in the car might experience as force pushing them back into their seats. When changing directions, we might call this nonlinear acceleration, which passengers might experience as a sideways force. If the speed of the car decreases, this is an acceleration in the opposite direction of the vehicle, sometimes called deceleration. Passengers may experience deceleration as a force lifting them away from their seats. Mathematically, there is no separate formula for deceleration, as both are changes in velocity. Each of these accelerations might be felt by passengers until their velocity matched that of the car. Definition and properties. Average acceleration. An object's average acceleration over a period of time is its change in velocity divided by the duration of the period. Mathematically, instantaneous acceleration. Instantaneous acceleration, meanwhile, is the limit of the average acceleration over an infinitesimal interval of time. In the terms of calculus, instantaneous acceleration is the derivative of the velocity vector with respect to time. It can be seen that the integral of the acceleration function a is the velocity function v, that is, the area under the curve of an acceleration versus time graph corresponds to velocity. Given the fact that acceleration is defined as the derivative of velocity v with respect to time t, and velocity is defined as the derivative of position x with respect to time, acceleration can be thought of as the second derivative of x with respect to t. Units acceleration has the dimensions of velocity divided by time, i.e., L, t2. The SI unit of acceleration is the meter per second squared. This can be called more meaningfully, meter per second, as the velocity in meters per second changes by the acceleration value every second. Other forms. An object moving in a circular motion, such as a satellite orbiting the Earth, is accelerating due to the change of direction of motion, although the magnitude may be constant. When an object is executing such a motion where it changes direction, but not speed, it is said to be undergoing centripetal acceleration. Oppositely, a change in the speed of an object, but not its direction of motion, is a tangential acceleration. Proper acceleration, the acceleration of a body relative to a free fall condition, is measured by an instrument called an accelerometer. In classical mechanics, for a body with constant mass, the acceleration of the body's center of mass is proportional to the net force vector acting on it, where F is the net force acting on the body, m is the mass of the body, and a is the center of mass acceleration. As speeds approach the speed of light, relativistic effects become increasingly large and acceleration becomes less. Tangential and centripetal acceleration. The velocity of a particle moving on a curved path as a function of time can be written as, with v equal to the speed of travel along the path, and a unit vector tangent to the path pointing in the direction of motion at the chosen moment in time, taking into account both the changing speed v and the changing direction of ut. The acceleration of a particle moving on a curved path can be written using the chain rule of differentiation for the product of two functions of time as, where n is the unit normal vector to the particle's trajectory, and r is its instantaneous radius of curvature based upon the osculating circle at time t. These components are called the tangential acceleration and the normal or radial acceleration. Geometrical analysis of three-dimensional space curves, which explains tangent, normal and binormal, is described by the Frenet-Serret formulas. Special cases. Uniform acceleration. Uniform or constant acceleration is a type of motion in which the velocity of an object changes by an equal amount in every equal time period. A frequently cited example of uniform acceleration is that of an object in free fall in a uniform gravitational field. The acceleration of a falling body in the absence of resistances to motion is dependent only on the gravitational field strength G. By Newton's second law, the force F acting on a body is given by, due to the simple algebraic properties of constant acceleration in the one-dimensional case. There are simple formulas relating the quantities displacement s, initial velocity v0, final velocity v, acceleration a, and time t, where equals displacement equals initial velocity equals final velocity equals uniform acceleration equals time. In the case of uniform acceleration of an object that is initially moving in a direction not aligned with the acceleration, the motion can be resolved into two orthogonal parts, one of constant velocity and the other according to the above equations. As Galileo showed, the net result is parabolic motion, as in the trajectory of a cannonball, neglecting air resistance. Circular motion. Uniform circular motion, that is constant speed along a circular path, is an example of a body experiencing acceleration resulting in velocity of a constant magnitude but change of direction. In this case, because the direction of the object's motion is constantly changing, being tangential to the circle, the object's linear velocity vector also changes, but its speed does not. This acceleration is a radial acceleration since it is always directed toward the center of the circle and takes the magnitude, whereas the object's linear speed along the circular path. Equivalently, the radial acceleration vector, the acceleration and the net force acting on a body in uniform circular motion are directed toward the center of the circle, that is, it is centripetal, whereas the so-called centrifugal force, appearing to act outward on the body, is really a pseudo-force experienced in the frame of reference of the body in circular motion, due to the body's linear momentum at a tangent to the circle. With non-uniform circular motion, i.e., the speed along the curved path changes, a transverse acceleration is produced equal to the rate of change of the angular speed around the circle times the radius of the circle. That is, the transverse acceleration is directed at right angles to the radius vector and takes the sign of the angular acceleration. Relation to relativity. Special relativity. The special theory of relativity describes the behavior of objects traveling relative to other objects at speeds approaching that of light in a vacuum. Newtonian mechanics is exactly revealed to be an approximation to reality, valid to great accuracy at lower speeds. As the relevant speeds increase toward the speed of light, acceleration no longer follows classical equations. As speeds approach that of light, the acceleration produced by a given force decreases, becoming infinitesimally small as light speed is approached. An object with mass can approach this speed asymptotically, but never reach it. General relativity. Unless the state of motion of an object is known, it is totally impossible to distinguish whether an observed force is due to gravity or to acceleration. Gravity and inertial acceleration have identical effects. Albert Einstein called this the principle of equivalence, and said that only observers who feel no force at all, including the force of gravity, are justified in concluding that they are not accelerating. Conversions.